let's look at how the weight of a wooden block affects the amount of friction force that wooden block experiences with the surface that it's sliding across. So to save you some time, I've already calculated a graph, and it looks like this. Let's talk about what this means, how I collected it, and then what it means. Step one, I took the weight of the block itself, calculated it in newtons, and then I pulled on it. And I pulled on it at a constant velocity, a sliding constant velocity. And for a single weight of a block, I calculated a single amount of friction force. So the pulling force directly opposes the friction force, and they're balanced because I'm going to go at constant velocity. And each time I do that, I get a data point on here. Let's start with the orange data points. So this first orange data point was the lowest amount of weight on the block. It was the bare block, and the amount of friction it experienced, it was somewhere around 3 newtons of force. Then I added weight to the block and repeated. I pulled again. And that heavier block experienced slightly more friction. So that heavier block, about a weight of 20 newtons, experienced a friction force of just over 5 newtons. And I repeated again. I put more weight on the block, and I pulled at a constant velocity and recorded that amount of force. And what you see here, for every time I did that, these orange dots stack up to be a nice linear looking set of data. Then I repeated it again, and instead of using a wooden block, I used a brick. So a different surface. It is really similar to this sandpaper surface. So sandpaper slowly increased the weight of the block, pulled it at a constant velocity, and I get this linear looking set of data, these purple dots here, that also appear to go in a straight line, but appear to go with a greater slope. Okay, that graph is now super important. I'm going to introduce a new idea using that graph that was experimental data from this block. And here you go. Let's talk about the slope of the line that connects these dots. I'm going to start with the orange one. And the line that connects these dots. You may have noticed, by the way, that in physics, a lot of the meaning we're making is about understanding the slope of a graph. Here goes. That line has a slope. Let's see here. We can approximate it. I'm going to use the point 0, 0, and the point which is about 40, 10. I'm going to calculate that slope. Let's see, 10 over 40, 1/4, 0.25. And because that's a force in newtons divided by another force, also in newtons, this number has no units to it. That line has a slope of 0.25. The other line, through the purple dots, has a greater slope. I'll leave that as an exercise to you to work out, figure out what the slope of that purple line is. Definitely bigger than 0.25. That slope has a very important physical meaning for friction. Now let's dive into that. I'm going to scroll and encourage you in your packet to follow along. Come down with me to the top of page 14. I've drawn a force diagram of my wooden block as I pull it across the table. So, or the track or whatever, as you pull it across some surface. I'm going to pull it. I have a gravitational force, a normal force. They balance. We're not accelerating up and down. I have a tension force pulling and a friction force resisting. They balance because in that experiment, the block is moving at a constant velocity. That graph had a slope that was this amount of force. Let's see here, highlight it. This amount of force divided by this amount of force. Normal over friction force. That number has a really important name, and here goes. It's called the coefficient of friction. There you go, coefficient of friction. We're going to use the Greek letter mu to represent it. Mu. It's like a U with a tail on the front end. That is a measurement that relates essentially a relationship between the surfaces in contact. Mu is often a number given to you. We're going to learn how to work with that now. So I want to point out that we've been talking about how heavy the block is, but the actual weight of the block is not the important thing. It's the size of the normal force. So that's what this next paragraph names. One subtlety needs to be made, and then we'll have an equation for friction. Friction isn't precisely dependent on the weight of an object. You know this because the ground might feel more slippery if you're on a slope, even though your weight hasn't changed. Instead, friction is actually dependent on the normal force acting on the object. Here's our equation. Friction force equals coefficient of friction times normal force. Here equals here times these two. We're going to do an example now. Make sure you understand this idea. What is the static friction force between a cardboard box and the rough wooden pallet it sits on? If the cardboard box and its contents has a mass of 15 kilograms, the coefficient of static friction between those two surfaces is 0.5. I always recommend begin with the equation. So write that down. F equals mu Fn. What is the static friction force? I'm solving for FF. I need mu and I need normal force. I have mu. It's given in the statement of the problem. I need normal force. Let's draw a force diagram. Normal, gravitational. They're balanced, meaning that's true. And if that's true, that's true. If Fn equals Fg, oh, but wait, I know Fg. Let's calculate the weight of the box. 15 kilograms. I presume this is happening on Earth. 15 times 9.8. 147 newtons. Back to my original equation. FF is mu times Fn. Friction force is half of that number. That's how you solve a straightforward friction problem. I'd like you now to move into problem set 2 and begin working these problems. As you'll see, in many of them, mu is given. That's not always true. Sometimes I'll give you the other information and ask you to solve for mu. Best of luck solving these problems. Thanks for your attention.